Hello, everyone. I hope you're all safe and sound. Welcome to the 12th lecture on analog and digital electronic circuits, in which we will study DC biasing of MOSFET amplifiers. So after quickly reviewing the need for biasing of an amplifier, I will discuss different biasing schemes. In fact, we will study these 6 different biasing schemes for MOSFET amplifiers. And then I will lay down some guidelines for analysis of MOSFET circuits at DC in general. And then I will end this lecture with a work example. So we know that MOSFET is a nonlinear device and it acts as an amplifier when it is operated in the saturation mode, in which the drain current, which is also called the saturation current, depends quadratically, has quadratic dependence on the gate to source voltage. So the purpose of biasing schemes is to ensure that MOSFET operates in the saturation mode if it is to be used as an amplifier. One important property of any biasing scheme is the stability of the resulting bias point against temperature or manufacturing induced variations in the device parameters. So it is very important in an amplifier circuit that the bias point remains stable against variations in the device parameters. These variations could be induced by changes in temperature or by changing the device in the circuit. A good biasing network will ensure high stability of the bias point against these parameter variations of the device. So the performance of any biasing circuit is gauged by the stability of the bias point against such variations. We will study different biasing schemes, and in the design and analysis of all of these schemes, we will assume that the resulting device, the underlying device is operating in the saturation mode. So we will use the expression for the saturation current to find the bias point of the underlying circuit. So the first biasing scheme is the fixed bias circuit, which is shown here. It's a very simple circuit, just consists of 2 resistors, the gate resistor and the drain resistor. So we know that the gate current for the MOSFET is 0. So this means that there will be no voltage drop across RG, which means that the potential or the voltage at the gate will be the same as the voltage at this node, and this node is connected to the power supply VDD. So the voltage VGS in the circuit is equal to VDD, and hence, since like I said, I'll assume that this circuit biases the NMOS in the saturation mode. The drain current is given by its saturation mode equation, which has quadratic dependence on VGS. So the drain current is then given by this expression, in which I have replaced VGS with VDD. And then by simply writing a KVL on the output loop, we can find VDS as VDD minus ID RD. So given RG and RD, we can find the bias point like this. We can turn this equation around and solve this equation for RD. So given the bias point ID and VDS, we can find the value of RD using this equation. Please note that since there is no current through RG, there is no drop across RG, then as far as the biasing of the circuit is concerned, RG is independent of the bias point. Later on, we'll see that for different amplifier configurations, RG will determine the input resistance of the amplifier. But as far as the biasing is concerned, RG can have any arbitrary value. It is independent of the bias point. So, well, then you might ask, why do we need RG at all? Well, we cannot leave this gate terminal dangling. We cannot leave this open. We have to connect it to one of the points in the circuit. We cannot leave this open. So if the voltage in this configuration, the gate is VDD, then why can't we just simply short circuit the gate to the supplier? Well, because if I directly short circuit the gate with the supply voltage VDD, then under AC conditions, when I short circuit VDD to ground, gate will be at AC ground. And since input is applied, the small signal input for the common source and common gate configurations, as we'll see later on, it will be applied at the gate. So that will short circuit the input source if the gate is at AC ground. So to ensure proper coupling of the input signal, small AC input signal, and proper DC voltage at the gate terminal, we use this RG. We cannot just directly short circuit gate to VDD. We have to connect this RG for proper coupling of AC and DC voltages at the gate. So this is a very simple scheme, but it's not a very good biasing scheme. It is highly unstable against variations in the device parameters because VGS is fixed. VGS cannot change. So any change in ID induced by changes in the parameters of the device, they cannot be countered by VGS. So this scheme is highly unstable against variations in the device parameters. Moreover, since VGS is fixed, the gate voltage cannot assume any other value as may be required by the design, because in this configuration, VGS is a fixed VDD. And like I said, RG can have any arbitrary value as far as the biasing of the amplifier is concerned. So the next scheme is a modified version of fixed bias. It is called fixed bias with source feedback. And as you can see that it is the fixed bias circuit, but augmented with the source resistance RS. So because of the zero gate current, the voltage here at the gate terminal is again equal to VDD. But since source is not grounded anymore, VGS, which is given by VG minus VS, is equal to VDD minus IDRS. So this time VGS has a dependence on ID. And ID in turn is given by this saturation expression, in which I have replaced VGS with VDD minus IDRS. You can open the square and rearrange the terms, and you'll find this quadratic equation. So we can solve this equation using this expression, in which A is RS squared, this term is B, and this term is C. So putting A, B, C in this expression, we can obtain two solutions for ID. One of them will be extraneous and will be discarded. The other one will be used to find VDS through this relation, which is obtained by writing KVL at the output loop in the output loop. So you can see that we can qualitatively analyze that this circuit has much better stability against variations in the parameter of the device. So if let's say because of the variations in the parameters of the device, if ID increases, then from this relation you can see that VGS will decrease. So because IDRS will increase, source voltage will increase, and since gate voltage is fixed at VDD, VGS will decrease. When VGS decreases, ID will decrease because ID has quadratic dependence on VGS. So this negative feedback provided by the source resistor, which is what gives this circuit its name. This negative feedback helps in maintaining a stable drain current, and as a result, it helps in maintaining a stable bias point. And given the bias point, ID and the VDS, we can design the circuit by finding the values of RS and RD through these expressions. As before, RG has no drop across itself, so RG is independent of the bias point and hence can assume any arbitrary value as far as the biasing of the circuit is concerned. But RS can be found by dividing the voltage at the source with the drain current, VS over ID. VS is equal to voltage at the gate, which is VDD, minus VGS. So knowing the voltages in the circuit, we can find RS through this relation, that is VDD minus VGS over ID. And then we can invert this expression to solve for RD. So given the bias point and the value of the source resistance from this expression, we can find RD. So you can use these set of equations to analyze and design the fixed bias circuit with source feedback. So the next circuit is the drain feedback bias. So in this case, instead of connecting this end of RG to supply, we connect it with the drain terminal. So since there is no gate voltage, there is no gate current, the voltage across RG is 0 again, which means that the gate has the same potential as the drain. So VG is equal to VD, which means that VGS is equal to VDS. So VGS is the same as VDS. And since VDS is given by VDD minus ID RD, so VGS is also given by VDD minus ID RD. So again, you can see that VGS has a dependence on ID. So any increase in ID because of some variations in the parameter of the device will decrease VGS, because increase in ID will increase the drop across RD, which will decrease the drain voltage and hence will decrease the gate voltage. Then source is at ground, decrease in gate voltage will decrease VGS. So increase in ID will decrease VGS, and then because VGS ID has quadratic dependence on VGS in the saturation mode, decrease in VGS will decrease ID. So this time in this circuit, the feedback, the negative feedback is provided by the drain resistance. That is why it is called drain feedback bias. So this negative feedback helps in maintaining a stable drain current, and as a result, it helps in maintaining a stable bias point. So ID is again given by this quadratic relation, in which I have replaced VGS with this equation, VDD minus ID RD. And again, opening up the square and rearranging the terms, we get a quadratic equation which can be solved by this using this expression, in which A is RD squared, this term is B, and this term is C. And then using one of the roots of this equation as ID, we can find VDS using this relation. So RG again is independent of the bias point, and we can invert, given the bias point, we can invert this expression to solve for RD. So given ID and VDS, we can find RD. So you can use these set of expressions to analyze and design the drain feedback bias. We can augment this drain feedback bias circuit with the source feedback, with the source resistance, which is also called the source degeneration resistance. And you can see that the resulting circuit, which is now aptly called drain source feedback, it provides negative feedback through RD and RS to keep the drain current stable. Because again, when ID increases because of some parameter variations, then the drop across RD will increase, which will decrease the drain voltage, which is equal to the gate voltage. So gate voltage will decrease. Also, the drop across RS will increase, which will increase source voltage. So gate voltage will decrease, source voltage will increase, and both of these will decrease VGS. So as VGS decreases, ID will decrease again. So this time the negative feedback is provided by RD and RS, and it helps in maintaining a stable current and a stable bias point in this circuit. So as before, VG is the same as VD because there is no drop across RG, and which means that the drain to source voltage is the same as gate to source voltage, and drain to source voltage is given by writing a KVL in the output loop. So it is VDD minus ID RD minus ID RS, and then we can use this VGS in the saturation current equation to find ID. So again, you can open up the square, and you'll get a quadratic equation which can be solved by this expression, using this expression in which A is given by the square of the two resistances RD and RS. This term is B and this term is C. So using one of the roots of this quadratic equation as ID, we can find VDS through this relation. In addition to, so previously in the previous schemes, we noticed that RG was independent of the bias point, but in this case, one of these two, in addition to RG, one of these two resistors is also independent of the bias point, because we just have this one equation at the output to find RD and RS. So we can assume, for instance, an arbitrary value as far as the biasing of the circuit is concerned. We can assume an arbitrary value for one of these two resistors and then use this expression to find the value for the other. So by assuming, for example, an arbitrary RG and an arbitrary RS, we can find RD using this expression. So given the bias point ID and VDS, we can find one of these two resistors by assuming the value of the other. The next scheme is a voltage divider biasing network without source key generation. So in the previous schemes, for example, in this one and in this one, the control over the gate voltage is not very well defined. The gate to source voltage is the same as the drain to source voltage, and in this case as well. And in the other two biasing schemes, there is no control over the gate voltage. The gate voltage is equal to VDD in this scheme as well as in this scheme. So by using the voltage divider biasing network, we get much better control over the gate voltage and hence the gate to source voltage. So again, this gate current is 0, which means that this VGS is given by the voltage division of VDD across R2. So that divided voltage is R2 over R1 plus R2 into VDD. So that is the voltage at the gate terminal. And since source is grounded, so voltage at the gate is equal to VGS. So VGS is set by VDD, R1 and R2, and hence it gives us much more control. Because of R1 and R2, we get much better control over VG and VGS. So putting this value of VGS into the expression for saturation current, we can find the drain current. By D, we can obtain VDS using this relation. And then I can invert this relation. So given the bias point ID and VDS, I can invert this relation to solve for RD. So in this case as well, just like before, when we had arbitrary values for RG as far as the bias point is concerned, here again, as far as the bias point is concerned, R1 and R2, one of these two resistors is independent of the bias point. So we can choose a value for one of these two, for example, R1, and then R2 is found through this relation. So given the DC voltages, VDS, ID, and VGS, we can assume the value for one of these two resistors, R1 and R2, and then we can find the other using this expression for VGS, and we can find RD using this expression, which is obtained by writing KVL in the output loop. So in this case as well, although we get better control over VGS, but still VGS is fixed at a fraction of VDD, and so it is fixed. I mean, we can control it, but VGS does not have any dependence on ID. So this configuration, because VGS does not have any dependence on ID, any changes in ID brought upon by variations in the parameters of the device, they cannot be countered by VGS. So this configuration is unstable against variations in the parameters of the device, which is why we augment this configuration with the source degeneration resistance. So in this circuit, you can see that the gate voltage is not equal to VGS anymore. So gate voltage is still given by the voltage division of VDD across R2. So gate voltage is given by this expression, and gate voltage is equal to VGS plus the drop across RS. So VG is equal to VGS plus ID RS. In other words, VGS will be equal to VG minus ID RS. So once given the value of R1 and R2, once we find VG, we can find VGS in terms of ID. So since VGS depends on ID, this circuit has much better stability against variations in the parameters of the device. So we can see that any increase in RD, so any increase in ID. So if ID increases because of some variation in the parameters of the device, then VS will increase. The voltage drop across RS, it will increase. So as VS increases, since VG is fixed, it is set by R1, R2, and VDD. So increase in VS will decrease VGS. So as VGS decreases, ID will decrease again, because ID in the saturation mode has quadratic dependence on VGS. So this source, this negative feedback provided by the source resistance will help in maintaining a stable bias point in this circuit, which is why this is the most often and commonly employed biasing network for MOS amplifiers. Not only it gives us much better control over the gate voltage, it also generates a stable bias point. So ID, given the biasing circuit, is again given by this expression, quadratic expression, in which I have replaced VGS with VG minus IDRS. You can open up the square and rearrange the terms. You'll get this quadratic equation, which can be solved using this expression, in which A is RS square, this term is B, and this term is C. So again, using one of the roots of this equation as ID, we can find VDS using this relation. So this expression again is obtained by writing KVL at the output in the output loop. So VDS is VDD minus the drop across RD minus the drop across RS. So given ID, we can find VDS. So given the circuit, we can find VDS and ID and VG using these expressions. So on the other hand, if we are given the bias point ID, VDS, and the voltage VGS, then we can invert this relation to find the value of RD, which is given by this expression, in which RS is obtained by finding the voltage drop across RS and then divided by ID. So voltage drop across RS is the source voltage, which is given by the gate voltage minus VGS. So gate voltage is VGS plus VS. So VS is then VG minus VGS. So source voltage is VG minus VGS. So given ID, VDS, and VGS, we can find RS and RD using this set of equations. And as was the case before, we can take one of these two resistors, R1 and R2, to be independent of the bias point, and then the other is found using this expression. So, so far we have assumed that the circuit, the biasing circuits, they ensure that the MOSFET operates in saturation mode. But in general, DC circuits could have MOSFETs operating in any mode, either in the saturation mode or in the triode mode, or even in the cutoff mode, depending upon the conditions of the circuit. So I am going to list down some guidelines that you can use to find the underlying mode of operation of the device, which will allow you to use appropriate expressions for the drain current for the analysis of the MOSFET circuits. So for an NMOS device, we know that NMOS starts conducting when VGS is greater than V threshold. So for an NMOS device, if you find the voltage VGS to be less than V threshold, or if you find the voltage at the gate to be less than V threshold, then you should consider the device to be in the cutoff mode, and ID will be 0. Otherwise, NMOS will be in the on state, and in the on state, it can either be operating in either the triode mode, can be operating either in the, it can operate either in the triode mode or in the saturation mode. So assuming that NMOS is operating in the saturation mode, you can find the drain current and the drain to source voltage using these relations. In which, depending on the circuit, because we have seen circuits in which RS is 0, so RS may be 0 depending on the circuit. So once you have found the bias point, you can check the voltage of the drain with respect to the source. If VDS exceeds the overdrive voltage, or if you were able to find the drain voltage and it exceeds this quantity, VG minus V threshold, then you should indeed consider MOSFET to be operating in the saturation mode. Otherwise, you should consider that the MOSFET is operating in the triode mode, and you should recompute the bias point at the DC voltages and currents in the circuit by using these expressions. This is the equation of the drain current when the MOSFET is operating in the triode mode, and then using this drain current, you can find the drain to source voltage. Following these guidelines, you can analyze any MOSFET circuit at DC in general. For PMOS circuits, all you need to do is replace these operators, this, and this, and this, with their inverse. That is, you need to replace this less than equal to sign with greater than equal to sign, and this greater than equal to sign with the less than equal to sign. For PMOS circuits, and you can use the same guidelines for analyzing PMOS circuits at DC. So as an example of a PMOS circuit, here I show a voltage divider network, which is being used to bias this PMOS amplifier. So remember, for PMOS, the direction of the current and the polarities of the voltages, they are opposite to that of the NMOS. So the drain current, which is equal to the source current. So in case of PMOS, we take the source current. So source current flows into the source. Power supply is connected to the source terminal through the resistance RS, and instead of VGS, we have VSG. So VGS for PMOS is negative quantity. So in order to put all of this in perspective, here I am going to work out this voltage divided by NMOS amplifier. So I'm going to assume that the supply voltage is equal to 1.8 volts, and the threshold voltage for the device is 0.4 volts. Furthermore, I will assume that the aspect ratio is given by this figure, 27.77, and the process transconductance is 200 microampere per volts. So we are given the resistance values R1, R2, and RS, and then we will solve the circuit for two different cases of RD. So since this is voltage divider biasing network, the gate voltage is given by a fraction of VDD, and the fraction is R2 over R1 plus R2. So plugging in the value, you find the gate voltage to be 1.286 volts. So since the gate voltage is greater than the threshold voltage, following the guidelines, I'm going to assume that the NMOS is in the on state. It's not in the cutoff mode. So it can either be in the saturation mode or in triode mode. So assuming that the device is in saturation mode, we can obtain the following two values for the drain current using the expression for the drain current, which I introduced in 11, using this expression. Because I'm using this circuit, so using this quadratic equation, I can find two roots for ID. So ID is, the two roots are 1.66 milliamperes and 0.47 milliamperes. So only one of these is valid. The other one is the extraneous. So we can find the extraneous root by observing that if I consider ID to be 1.658 milliamperes, then ID RS, the product of, because RS is 1 kilo ohm. So ID RS comes out to be 1.658 volts, which gives VGS, which is equal to VG minus IDRS, to be equal to minus 0.372 volts. So this suggests that the NMOS is in cutoff mode because threshold voltage is 0.4 volts and VGS is minus 0.372 volts. But we've already established that the NMOS is in the on state. So this must be the extraneous route. So we discard this route and we take this value as the drain current ID. So now having found out the drain current, we find the output drain to source voltage for two cases of RD. Remember, we are still assuming that the NMOS device is in saturation mode. We haven't established that it is in saturation mode. It is still an assumption. So in order to establish, we need to find out VDS, and we find VDS for two different cases of RD. So in the first case, I assume that RD is 1 kilo ohms. So using this value of ID, I can find the drain voltage. So the drain voltage is given by VDD. Voltage here is given by VDD minus IDRD. So this comes out to be 1.327 volts. So this voltage, so using this number here and the threshold value, we can see that since the threshold voltage is 0.4 volts, 1.286 minus 0.4 is 0.86. So this expression, this value is 0.86 and VD is 1.327. So following the guidelines, this establishes that the device NMOS is indeed operating in the saturation. So using this value of RD, for the circuit in which RD, for this circuit in which RD is 1 kilo ohms, the drain current of 0.473 milliamperes, gate voltage of 1.286 volts, and the drain voltage of 1.327 volts. They place the NMOS, underlying NMOS, in the saturation mode. However, in the other case, if I take RD to be equal to 3 kilo ohms, then using this route, this 0.473 milliampere value, I can find VD again, and this comes out to be equal to 0.38 volts. And this is clearly less than VG minus V threshold, which was about 0.8 volts. So this suggests that VD is less than VG minus V threshold if we use this valid route for the drain current. Hence, our assumption that the NMOS is in saturation mode is invalid. So we must assume that the NMOS is in triode mode. So this establishes that the NMOS is in triode mode. So once we know that NMOS is in triode mode, we must recompute the drain current, because this drain current was computed using the saturation expression, the expression for the drain current in saturation mode. But now that we have established that the NMOS is in triode mode, we should recompute the drain current using the triode mode equation. So you can open this square up. Again, this is a quadratic equation. We know all the values of the resistors. We know the threshold voltage. We know the process transconductance, the source voltage, W over L. We know VG. So we can solve this equation using the quadratic formula. And again, we'll get two routes, one of which will be valid and the other one will be extraneous. How do we find the valid route? So let's analyze this first solution. So for this, our ID, when ID is equal to 15.62 microamperes, we can recompute VGS minus V threshold. So VGS is equal to VG minus IDRS. So VGS minus V threshold is VG minus IDRS minus threshold. So we know VG, we're taking ID to be equal to this value. We know RS, we know V threshold. We solve this and we get 0.87 volts. And corresponding to this drain current, we compute VDS. So VDS is VDD minus the drop across RD and RS. So VDS is equal to this expression, which is, by putting in the value of ID, comes out to be 1.73 volts, 7.74 volts. So this shows that since 1.74 volts comes out to be greater than 0.87 volts, using this value of ID, VDS comes out to be greater than the overdrive voltage, but which suggests that if this is the current going through NMOS, then the NMOS is in saturation mode. But that is incorrect because we have already established that the NMOS is in triode mode. So we discard this route. This is the extraneous route. And we take this route as the value for the drain current. So for this drain current, we can find the VGS again. We can find VGS minus V threshold again using this expression. This comes out to be 0.483 volts. And we can find VDS again using this expression, which comes out to be 0.188 volts. Since VDS is less than VGS minus V threshold, so this value of drain current correctly identifies the NMOS to be in the triode mode. So using those set of rules, you can analyze any given MOSFET circuit at DC like this. So this brings us to the end of this lecture. Thank you very much for your time, and I will see you in the next class. Take care.